everyone? Very good, very good. Well, I'm Chris Sorensen. I'm a professor of physics. I've been here for 37 years, sort of time immemorial. Thank you very much. So let me ask you a question. Are you ready for a little physics? All right, yeah, that's what I want to hear. Okay. You know, science, physics certainly to some degree, but science in general pervades our civilization. We've got cars, we've got airplanes to move us around the surface of the earth. They're above the surface of the earth, and they're the product of good science. You could go out to Pikes Peak, stand on the top of Pikes Peak, and talk to your cell phone and ask it how to get to Forum Hall on the campus of Kansas State University in Manhattan, and it will tell you how to get there. Isn't that just amazing? Yeah. And let's not forget medicine too, right? The products of science. It extends our lives, it enhances our health. All these things are a result of good science. And yet, typically, when you ask somebody about the methods of science, they really don't know how it works. They'll know facts about science, but not the methods. And the methods are very important because we have some very important problems in front of us. Numerous problems facing society and civilization. For instance, is global warming due to man-made activities? Or what's the difference between creationism and evolution? Things like that. Without understanding the methods of science, we can't address problems like that in a coherent manner. And indeed, you're all undergraduates, or most of you are certainly, or you've been to undergraduate school, and you take science classes in undergraduate, and you learn certain facts and so on. But it's sort of remarkable to look back perhaps at your training that very often when we teach science, we teach it in a dogmatic manner, right? That's not the way to teach science. You need to teach the method of science. I sincerely believe that it's extremely important that when students go out into the world that they can address problems that are essential to our civilization and address them with the methods of science. Now tonight what I want to do is give you an example, what I consider a beautiful example of the method of science, or what I really like to say it as, how we know what we know. And my message isn't so much the content of what I'm going to tell you, but the method itself. And true, I'm addressing this to the student, or perhaps even more so to the teachers of science. It's up to us as teachers of science to explain science in a coherent manner and to make sure that our students know the methods of science. So let me begin. There's my great question. What are stars? Oops. I went the wrong way, right? Do you remember the Moody Blues? Something out of my era. Are they pinprick holes in a colorless sky? What are they, where are they, and how far away are they? Certainly this is an ancient question. Been around for a long time. We can imagine early Homo sapiens wondering about such things. In regarded history, we know that the Greeks were the first to start worrying about things in a manner that we have recollection of. And one of the things the Greeks first noticed is the concept of parallax. Parallax is when you drive down the road and you see the fence post going by really quickly, and then maybe a more distant tree slips by at a slower rate, and then a more distant farmhouse even slower. The further things are away as you move across the landscape, the less they seem to move relative to the background. The Greeks recognized well that if they moved, say, from Athens to Spartan, and they looked at the stars, they didn't seem to move relative to each other, which implied one of two things. Either the stars were very, very far away, or they were all the same distance away. Which are they? Well, subsequently, we can use the method of parallax once we realize, according to Copernicus, that the Earth is in motion too. It goes around the sun once a year. And in July, the Earth is on one side of its orbit, and then 6 months later in January, it's on the other side of its orbit. And now we've got this big distance, 2 so-called astronomical units to view the stars with. And if we see a parallax then, we can measure the distance. As it turns out, there is a parallax. It's a very tiny parallax angle, like on less than a second of arc. And a second is a 60th of a minute, and a minute is a 60th of a degree. So you can see how small that angle is. Here's an example of parallax. We got two guys here at positions A and B looking at some treetop, and this fellow sees it relative to this mountaintop, and this fellow sees it relative to that mountaintop. Now, if we apply this method of parallax to the stars, we can actually measure the distance to the stars, and here's a result you probably knew, but again, I want you not to know just the facts. I want you to know how we got the facts, and we get it from a parallax measurement that the stars are very far away indeed. Matter of fact, it was just 2 nights ago I was on the top of some boat in the South Atlantic, and I managed to see Alpha Centauri, the nearest star, some 4 light years away. The time it would take light 4 years to travel to us from that star. Other stars up here, well-known Sirius, the Dog Star, and so on, all more than light years away. Now, there's our first knowledge about stars. We now have some idea where they are, but how far? Well, another thing that we can get from stars is their brightness. Stellar brightness is measured by magnitude. Here you can see the constellation Orion, and we've got the belt stars that are second magnitude, and then Betelgeuse and Rigel are like first magnitude. The smaller the number, the brighter the star. But the problem becomes that's an apparent brightness. What's the absolute brightness of these things? But if you think about it a little bit, if you know the apparent brightness and if you know the distance, you can back out the absolute brightness, accounting for the distance, and that's the number that we call the absolute magnitude. So what does this absolute magnitude depend upon? Well, let's think about it a little bit. If we have some luminous object, what would make it bright? Well, certainly its size, right? A big light bulb is brighter than a small light bulb. So that's the first thing I expect. And then the second thing I expect is its temperature, right? A hot light bulb or a hot iron might be brighter than a cold one. So let's look at both of these things, right? Size and temperature. And here's a neat thing about temperature. You can see somebody has pulled his horseshoe out of a hot furnace, and look at it glowing here in the darkness, one might say. Here it's hottest with the yellow hotness. Over here where the pliers is holding on, it's not very hot at all, so it doesn't appear to be glowing to us. But the glow increases, it gets brighter, but notice it also transforms from red to yellow. And if we did experiments in the laboratory, we would find that as the color goes from red into yellows, into whites, into blue, we get hotter and hotter and hotter. This is how we measure the temperature of molten steel, right? Can you imagine having a thermometer and sticking a glass thermometer in a molten steel trying to measure the temperature? No way, but by looking at the color brightness, we can determine the temperature. Now, here's Orion again, and what do you notice? Look at Betelgeuse compared to Rigel. What color? Yeah, what color? Which one's hotter? Rigel, yeah. And now we realize we can measure by color the temperature of stars. Now let's see where we are. We've got a measurement of color, hence temperature. We know their distance. We're making a heck of a lot of progress, right? We haven't drug any stars into our laboratory and tinkered around with them. They're far, far away. And yet we're gleaning their properties by these simple observations. Now, here's an interesting question. Are bluer stars brighter? Are redder stars dimmer? Right, we saw that red implied low temperature and blue implied high temperature, and high in temperature ought to be brighter. And what astronomers have done is they've plotted that absolute magnitude, the true brightness, versus a color temperature down here. So here's the hottest in blue, ebbing away into the coolest in red. And there's a bunch of spectral types here known as O, B, A, fine, girl, kiss me. Those astronomers have a lot of fun late at night. Okay? And what do we expect? Well, we expect that indeed bluer stars will be brighter and redder stars would be cooler, and we might expect a curve like that, right? Here's the red getting brighter and brighter until we're blue. We have to test this hypothesis. Let's go and look at the brightest stars. Here they are, plotted. Looks like a shotgun pattern, doesn't it? But you know, you got to look for patterns. That's another method of science. Let's take a close look at this. Right in here, there's a bit of that pattern we were predicting, right? Cooler, hotter, 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 and brighter. But then there's all this other stuff over here. But let's think about this. This is the brightest stars, correct? I mean, these are like the Obamas and the Raquel Welches. I had a thing for Raquel Welch, so excuse me. Of our country, right? We need a more random population. So one can go to the star catalogs and pick a page at random. And that's what I did. And I have them here plotted in purple. More of this correlation in here, but notice there's a glob of stuff starting to accumulate here. Then I got to thinking, well, even a star catalog picked at random are still probably amongst the brightest stars. What we need is like going to your old neighborhood and just picking all the kids on Charles Street in Omaha, Nebraska. That's a nice random sampling. Let's pick the nearest stars to us and see what we get. And here's the nearest stars. And now we have a magnificent correlation. And here's an example of how we know what we know. Look at this. We go from the reds, which are the coolest, along this so-called main sequence of stars until we get the hottest blue stars, also the brightest. But up here we have an ensemble of stars that are reddish, and yet they're very, very bright. Why would they be the same temperature and yet brighter? Because they're bigger. What should we call these big red stars? Red giants, and that's how we know red giants exist. What about these guys down here? They're white, but they're very dim. They must be very small. Yeah, let's call them red small guys. No, we'll call them white, or we'll call them white small guys. I'm sorry. Let's call them white dwarfs, and that's how we know that as well. Finally, most importantly, we've left somebody out. What about our sun? Here's where our sun lies, right in the middle of the whole thing. And what's this telling us? You're thinking it's telling us that the sun is a star. But I'm thinking it's telling us that all the stars are suns. And now we know what stars are, don't we? And that's how we know what we know. Thank you very much.